So following nicely from Paul's work, we're actually going to go back in time a little bit. This talk is mostly going to be a summary of a paper that was published back in 2021, written by my co-authors and myself, who are all up there. And this is actually going to be a discussion of those limb profiles that Paul was referring to. Yeah. So I'm mainly just going to do a real top level summary. There's not enough time to go into all the details of a 15, 20 page paper. I forget what it was. So the first big takeaway is, there is topography data out there. And that, extends past DMs, so that seems to be getting, changed. It's sort of pushing the limits of DMs now. And for those of you who might not know quite what we mean by limb profile or limb, I really like this picture of Karen because it shows how there's a bunch of topographic information right there on the body edge between the body and space. And so what is in the data set is actually all of the Lori approach images. There is one Lori image during the flyby that we managed to get a limb profile. New Horizons managed to tilt just the right way, and we were confident enough in that topographic information and the elevation there that we actually added it to the data set. Everything else is on approach. There's no MVIC data here. That's because MVIC has, since it was a scanning camera, we had some issues with the long wavelength information there that we sort of held on to them for the most part. All right. Link I put in the abstract, it's also in the paper. Go out there, use it. I just have a recommendation towards using it, and I would use it in conjunction with other information. So for example, in Alan Stern's Farside paper, Carver and I created a few limb profile topography sets for that paper. And in that paper, we were able to show that these albedo variations actually correlate with elevation changes, and we were able to, or Alan was able to, apply that to very specific processes that created those albedo variations. However, I also have some warnings when you go out and use this topographic data. Be careful when using it alone. For a good example of why you shouldn't use it when it's alone is limb profiles are biased towards higher elevation. Their higher elevation closer to or further away from the limb is going to peak out above. And I had to do a lot of work in this paper when I did actually use limb profiles alone, even though I'm warning you not to. I did do a lot of work showing that the apparent limbs don't have an effect on our big picture results. There's also some issues with the actual Pluto data set. Since we are sort of an albedo scanning algorithm, the wild changes in albedo can cause there to be some fuzziness, some deviations, and we tried our best to correct for most of those, but some of them did slip through. All right, so the very big, result we got from looking at the limb profiles by themselves is that when you take the topographic data, you end up, you have these nice long hordes of topographic data that you can throw through a Fourier transformation, get out topographic variance spectra, and you can, look at what you see or look at what you get. So Pluto's topographic variance spectra, this is only a 15-minute talk, so I can't quite, give all the details here, but Pluto's variance spectra, topographic variance spectra is very flat. And, we'll still find something interesting out of that, don't worry. But Karen's has this break and slope here at about 150 kilometers. And for the paper, we viewed this as a sign of a lack of support past 150 kilometers. So when Karen's topography, released topography that was captured in limb profiles was being generated, topography that was wider than 150 kilometers either sank or filled in slightly because Karen's ice shell could not support topography that high, right? And so what we did, I'm going to pass over this, is actually go and model what the topographic variance spectra should be for an idealized version of Pluto and Charon with different ice shell thicknesses, or rather different elastic thicknesses for the ice shells. We used the Turcotte 91 method, and we did this with and without membrane support. And the way I like to think of membrane support is, who here has ever gotten a dent in a table tennis ball? And who's tried to get it out just using their, like pushing it and using their fingers? No, you're not going to be able to do that. So that can actually apply on a global scale for, small enough bodies, where we have a coherent one piece ice shell. And so we did this analysis, with the membrane support and without. That's the dashed and solid line respectively. And for Pluto, it didn't really make a huge difference. And that makes sense because when you have a larger body, the membrane support is a smaller effect. And you can see that sort of in both cases, we'd only expect to see a break in slope on Pluto if Pluto's elastic thickness of Pluto's crust was less than 60 kilometers. You can get away with having a bit, or rather you need a bit thicker thickness in a case where you don't have this membrane support, however. Just something to keep in mind. We did the same thing for Charon. This is sort of the big piece of the paper. Because the weird thing about Charon is you really can't have any of that membrane support at all. Charon is not a ping pong, which might seem obvious in retrospect. But this wasn't super obvious to us when we were first doing these models, and Charon's model seems to work better without this spherical membrane support. And for the paper, we looked at this, threw it through some very simple, fit, and we got that the elastic thickness should be somewhere between 20 or 10 to 30 kilometers, which was quite thin compared to what we sort of think it is today. However, some way that my thinking of this paper and the study has changed is I'm kind of wondering if I looked at this the wrong way. And that, in terms of what these limb profiles sampled, were we looking at partial membrane support? And just mainly because of the way that this part of the variance spectra crosses sort of through multiple elastic thickness models. I'm going to hopefully have enough time to talk about this for later, but that is seeming to not be the case, so maybe approach me later. So a big part of or rather something I feel like I did not do a very good job in this paper explaining is, we get these two numbers, but are we talking about the same type of crust at the same period of time for these two bodies? And the answer is no. And I really feel like I did not do a good job explaining that. So hopefully I'll do a better job here. Because asking when and where do these two elastic thickness values apply is really important. For the when, going through very quickly, we look at, since we're looking at support, we think of this in terms of heat flow. And very specifically, at what temperature and based on temperature where you move from ductile to elastic, that actually allows you, if you model that, allows you to actually determine heat flux ranges for Pluto and Charon during topography formation for the limb profile topography. And this is sort of what we get, this is what we got for the paper. And these heat sources, these are the ranges we got for Pluto and Charon. And when we look at possible heat sources to explain those two ranges, for Pluto, it's radiogenic. You're getting down to a few milliwatts per meter square, especially on Pluto. In that limb profile topography, we're probably looking at more down here than we are necessarily up here. For Charon, we have no idea. It's all over the place. And to get this much heat, we're talking about tens to close to 100 milliwatts per meter squared. we start to have to invoke, these very early heat sources that that James was talking about this morning. And for the paper, we landed on tidal heating as being the likely culprit, but one of the things is since this paper has been published is sort of a pushback, and that I actually agree with, especially given the amount of unknowns with the tidal heating picture. All right. Regardless, for Karen, we are looking very early on in terms of the heat, right? And when I say geologically current for Pluto, I mean the topography is recording up to nowadays, right? And then the other question was, where do the results apply? For Pluto, as Paul was showing earlier, we're really mainly looking at this mid-latitude, heavily cratered, likely depositionally active terrain. But based on what we see in the high resolution and the low resolution imagery, there's not anything big going on, right? Not anything that would sample the full extent of the ice shell, especially not today. Whereas, in the past, there are, features like Ort and Edgeworth that Bill looked at that, are old, did likely record an earlier, more substantial heat flow period of Pluto. On Karen, we're looking at a much wider range with a lot more unknowns about what is actually going on over here. We have some really big mountains. We got some, pretty deep holes. Who knows really what's going on, but it seems to be a lot of tectonics relative to what we see on Pluto. A lot more, large scale stuff that could really only happen early on. So that sort of brings this whole picture together, right? So when you use those elastic thickness numbers, I want you to think about the where and the when, and make sure you don't sort of apply them very generally, like I may have, suggested in a paper. And I'm running short on time, but I'm going to try to go through this very quickly because I had a thought when I was, going through my results, and I was talking earlier about how Karen seemed to lack, or at least partially lack, this membrane support. And this is going to be very much an off-the-cuff hypothesis. And I'm wondering how much of that is evidence of Karen's ice shell being partially broken when that topography was recorded and set in place before large-scale freezing happened. Because when we look at what is sampled majority by these limb profiles is a lot of Ozterra. A lot of that very broken up, large crustal blocks, a bit of extensional tectonics going on. And I feel like there's something there that I just don't know how to put together as one solid story. And, I would love to get some input on that out there. I'm going to leave up the conclusions, and I see I only really have a minute for questions. So thank you very much.